and and the host needs to set that. Okay. And now I get to play. So, hi, this talk is called Combining Art and Astronomy. Um, so it's a mingling of cosmos and canvas. It could easily also be called um, just simply scientific visualization. My name is Jayanne English. I'm from the University of Manitoba, and I'd like to begin with a land acknowledgement. With their treaties, the First Nations and Métis, including the traditional owners of the Treaty One lands, where I now live and work, generously adopted my Jewish ancestors who were exiled by events in Europe. In the spirit of our aspirations to care for our planet and harmonize its peoples, reconciliation, and tikkun olam, I acknowledge and pay my respects to the Anishinaabe, Cree, Oji-Cree, Dakota, Dene, and Métis peoples and their ancestors. Wetaskawin, Shalom, proceed in peace, and Miigwech. Okay, so the format for this talk is based on a talk I gave to a company that creates statins, so medicine, and they have breakfast talks. And they ask some good questions. So I'm going to add in these good questions to my talk. My goal here is to provide an example of an interdisciplinary career from which you could possibly discover some tips if you also want to combine some other passion along with a physics passion. One of the questions that they asked, and you guys are in my way, so I'm going to close you down. One of the questions that they asked was, you focus on the creation of astronomy images. Is that because you have a talent for it, or you didn't like what was being created, or you saw an unmet need from an audience like the general public? Well, let's start here with the creation of astronomy images. And there's more than one kind of astronomy image that can be made. So the banner here for Zoom is a bit in my way. So I'm going to sometimes look at another version of my talk just so we can see. I can read the titles. So what I do is I use perception-based approaches to scientific visualization. So our eye and brain system create perception. For example, color. It's not a physical thing. It's based not just on wavelength, but on many things. And so our eye-brain system produces what we perceive. And we can work with the physiological components involved in order to communicate more clearly. And the kind of images I make are those that go out into the public. So they're called public outreach images. And you've seen them online or in magazines, whatever, all sorts of media. Another kind that I work with are for professional publications. So for journal figures and catalogs, and the creation of an image of, say, multiple different frequencies can help us learn whether, for example, in this case, star formation regions are causing synchrotron radiation out into the halos of galaxies. And instead of using contour plots, which are hard to tease out the information and it takes time to do it, at a glance, we can start to see whether there is a correlation. Also, I developed color tables that work with the eye-brain system for assigning colors to astronomy parameters, such as physical parameters like velocity. Okay, so let's go back to this question that they asked. And this is a question about outreach. they said, you focus on the creation of astronomy images. Is that because you have a talent for it? Or did you, um, hmm, you're, or you didn't like what was being created, or you saw an unmet need from an audience like the general public? So, what my answer is, for the short answer, this is a public outreach image that recently came out on Astronomy Picture of the Day. And what my short answer to this is, uh, I did it because of my background. So I'm trying to, there we go. So my answer to this is I fell into making public outreach images because I went to the Ontario College of Art and Design University. That's what it's called now. I'll refer to it as OCA. Um, uh, and after that, I went to the University of Toronto for a BSc in astronomy and physics. And then I skipped the master's and I went to the Australian National University for my PhD in astrophysics. I'm still an artist. I still make art and I collaborate with artists. This is an example from an art show that was not too long ago. I graduated 40 years ago, and this exhibit is by 40 people who graduated 40 years ago. And we were asked to create an image to put in the show that referred to a piece we made 40 years ago. And here you can see mine consists of a painting, sculpture, and video. And the video uses a public outreach image in the processing of how to make a public outreach image. Here's the image, here's the artwork that I made 40 years ago. So sculpture and painting. So I got a certification from the Ontario College of Art, and while I was there, it was in the New York City off-campus program where I worked in an art studio to create my work for the program, but I also took science classes, for example, math classes. Then I did remedial grade 13 in math while I was in on this art program. And so I recovered my math and physics because I hadn't done that in a while. And while I was a student at OCA, I had other OCA students and instructors perform a piece called A Visualized Cosmology in an astronomy dome on top of the McLennan Building at the University of Toronto. So you can see by the title that my artworks were astronomy based. Those were the themes. So then I went and did a Bachelor of Science, a double specialist degree in physics and astronomy at the University of Toronto. And there I also made my peers do art. We would go off to art shows. We'd all get in a van and go to Buffalo to look at the art. And we even made art together. So here we are, and all of us here, we're math and physics geeks, and we made the painting behind us. Then I did a PhD in astronomy and astrophysics at the Australian National University. This is the Parkes Radio Telescope. There's a really cool movie called The Dish if you want to check out this telescope. At the top here is the receiver cabin. Here I am at the receiver cabin, way up there. So I was training to be an observational research astronomer, and I used both radio and optical telescopes. And I encouraged my fellow grad students not only to make art, but to exhibit art. So my first public outreach image was a figure from my thesis. It was neutral hydrogen gas in a galaxy that consisted of two galaxies merging together. And it has long gas tails because of this interaction. And you'll be shocked at what it looks like. It looked like that. And they just pulled it from my thesis. I got a package in the mail that was like a little rectangular box. And when I opened it up, there was all these postcards of this image. And on top of it was a note that's from the director of the observatory at the time, Ron Akers, who said, Jayanne, my lawyers tell us we can be sued by you because we didn't ask your permission. But of course, it was wonderful, and they also made it into a Christmas card. It's got optical data, it's got infrared data, and it's got radio telescope data for these long gas tails. We call that tidal debris. I then did 2 postdoctoral fellowships. Those are kind of standard. Actually, at my time, 3 postdoctoral fellowships were standard. The research I was doing was with the Canadian Galactic Plane Survey that used the Dominion Radio Astronomical Observatory to the data from there, and we were looking at our Milky Way galaxy. It's out in Penticton. And I was studying this mushroom-shaped cloud. And this is when I started to explore making public outreach images. These are the first radio images that aren't contour plots, but rather have the qualities of optical outreach images. And I started to do that to describe my research. So here's a mushroom-shaped cloud, which theorists thought had to have a whole cluster of stars in the plane of the Milky Way to create something like this. And instead, we modeled it as if there was one single supernova explosion above the disk of our galaxy, and that could, we found, create this mushroom-shaped cloud. Simultaneously, I was on the board of directors of an artist-run center called Modern Fuel Gallery. And I there ran workshops called Soft Copy, Hard Copy, where I put scientists and artists together in pairs. And the scientists were asked to do art based on the science explored by the artists. And I curated that exhibit that came out of that workshop. But when I went to Space Telescope Science Institute for my 3rd postdoctoral fellowship, and that's the place that runs a Hubble telescope, my whole life got taken over by public outreach. So here's the Hubble Heritage team at the time. I'm the shortest one, of course. I was responsible for everything about this website. For example, I did the design of the logo. I designed the website. I authored the website. I did press releases. And these were all monthly. I was the project facilitator, and I trained everybody in how to make images. And they were very successful. And I put up this one because there used to be a magazine called Life Magazine, and it had a special image issue every year, which was the year in pictures. So this image made it into Life Magazine's special issue. That was quite an honor. When I then became a professor, I started, of course, as an assistant professor, then associate, and now I'm what's called a senior scholar. Sometimes we're called professor emeritus, but I'm just a senior scholar. So that means that I am now pseudo-retired. I do everything but teach, and I don't get paid. But, I still want to collaborate. And when I was first a professor, I started to collaborate with my colleagues. So any research team that I was on, I would take the data and make public outreach images for them. So I worked with radio telescopes and also optical, for example, especially the Hubble Space Telescope. So the breakfast group asked, there are likely many options for collaboration. How do you decide who to collaborate with? So an overview is that I'm invited into research collaborations. NASA asks me to visualize data, and I set up research collaborations. So for example, for being invited into research collaborations, I might be a co-investigator on observing proposals that are targeted on specific objects. I might be one of the many investigators that's part of a survey of the cosmos. Occasionally, my team requests someone's expertise, and in exchange, I will contribute to that person's team. And I will do that by making images for them too. And often principal investigators appreciate my visualizations and they invite me to participate in their team. And it would be easy to say no, but most of the time they present me with a visualization challenge that's fascinating, and I really can't resist those. Sometimes, besides NASA asking me to visualize data, which is more the way it usually goes, sometimes I incorporate NASA data into my collaborations, and I propose to Astronomy Picture of the Day that they might like to post these. And they do, especially if I will also write the blurb that goes with it. So I've also gotten into a bit of public outreach writing. Okay, and then I set up research collaborations and visualization, such as our project Cosmos Canvas, which I'm going to show you to you in a few slides. And this is one for color mapping parameters supported by human perception. And mainly now I'm organizing virtual reality visualization collaborations. This is a really nice object that uh, we discovered in one of the surveys. So I wasn't part of this team, though I knew Ray Norris, who made the discovery. So Ray said, Jayanne, come and make an image. And this is the work I do on Cosmos Canvas, designing. This is for velocity field, and I'll describe that shortly. So my contract as a professor was to do 40% research, 40% teaching, and 20% service work. Now you might have an idea what's involved in the other, in the 40% pieces, but the service piece, I'll just describe a little bit because it has a lot of components. So you are asked, it's not like you could, you will, if you're a professor, help develop curricula. You will end up serving on departmental and university committees. You'll serve on national and international committees. I like these. I was a panel reviewer for competitions, for grants, for fellowships, for time on telescopes, because it's very competitive to get time on telescopes, and other competitions. But you're also asked to do community work, such as public outreach, and this is meant to pique the public's interest in our research. And you can do this using talks or producing content for books, media, and websites. Well, let's start with the first one. How do I fold in visualization to that? Well, we want to make discoveries, and we can do analysis in different ways. We can do some math, we can make some models, or we can do some visualization to help us make discoveries in our observational or experimental data. So what we want to do for visualization is work with the iBrain system. So I want to point out what happens in the iBrain system. Now, you may know this already, but let's look at it. These circles are the same size. Which one appears to approach you or seems bigger? Which one comes towards you or seems bigger? If anybody wants to unmute and yell out an answer, that would be good. Okay.
Warm.
Which one?
The warm one.
The warm one, that's right. So the red one pops forward. And in art, we call anything that approaches, any color that approaches warm, and any color that recedes, we call cool. And of course, we all know temperature-wise with the black body curve that it's the opposite in physics, which is interesting. Okay, so when we're going to describe the velocity, let's say we have a galaxy that's rotating like this, and we have the Doppler shift. So as the gas is emitting radiation and the frequency comes towards you, it becomes higher pitched, and it goes, eh, and the part that goes away goes lower pitch, and the what part that's coming towards you is, because it's higher frequency, is towards the blue end of the spectrum, and the part that's receding away from you is towards the red end of the spectrum. Okay, with the lower pitch, longer wavelengths, if you like. Okay, so we can check whether a galaxy is rotating or not if one side is coming towards you and one side's going away. So visually, which part is popping forward here? Well, we said the red, but redshift is supposed to go away. So this little thing, we look at this and it's involved with our perception. So in our terms of perception, this, although it's blue shifted, is receding visually. And physically, it's supposed to be coming towards you. See, this looks like it's receding, and this looks like it's approaching, but this is red shifted, which is receding. Okay, what can we do about that? How can we support our message by using colors? Well, we can use this handy tool called a color wheel, and the complements are across the color wheel. And I've picked here a reddish color and a turquoise color. And I can make the turquoise color light, and I can make the reddish color darker over here on the right. I don't know if you're seeing my mouse or not. Hope so. And if I add a little bit of the turquoise to the red, thank you, then I get this color right here. And if I add a little bit, if I add a little bit of turquoise to the red, I get this color over here. If I add a little bit of red to the turquoise, I get this color here. And if I keep adding little bits of color and I do it right, and your monitor is calibrated, this color here will be neutral gray, okay? So this kind of scale is called a compensating tones color scheme. And the colors are selected visually. So if you're going to try this, it won't work if you use math and just add values together, because not only is your monitor nonlinear, so is your eye nonlinear. So you actually have to train yourself to see neutral gray and colors in order to make this work. So here was our previous color scheme where the red for redshift popped forward. Now we can make another one. Yay, now the red shift recedes and the blue shift approaches. And we look at, so we can use this to support the intended meaning using the perceptual effects. And so now when we look at NGC 3256, that little blue shifted cloud appears to be floating right towards us. And we can see the signature of rotation in this galaxy. And here's another one where you can see the signature of rotation in the galaxy. So it's going from red through systemic velocity out to its blue shifted coming towards you side. This work is done by Mark Richardson, Gilles Ferrand, and Nathan Degg for surveys such as changes and wallaby surveys on various telescopes. And you can check these color tables out by going to GitHub. You have to look for Cosmos Canvas, and it's under Mark Richardson's name. Okay, what else can I do with this color scheme? I can take this is now optical data, it's spectrographic data, and it's ionized hydrogen gas instead of neutral hydrogen gas. But you can see the rotation of this galaxy. One of the things I can do with this velocity field map is make all the colors to have the same intensity, the same brightness. So perceptually, they're equal values in terms of their brightness, not their vividness, but what their light or darkness is. And if I was to print this out in grayscale, it would just be a gray, solid one gray blob in the middle, not a variety of grays, but one solid gray. And the reason I do that is I want to put a grayscale image on top of that. And grayscale images have dark grays and light grays. And this way, you don't change a light gray to be darker or dark gray to be lighter. You just keep the correct intensity relationships when you have perceptually equal values in your color map. And so that means I can see that there's ionized gas that's away from the plane or disk of the galaxy. And I can also see one side of this halo gas is coming towards me and one side is going away. So it's rotating along with the galaxy's rotation. Here's another use of our velocity field map. We've taken a galaxy's neutral hydrogen gas and we've separated out the disk and a ring around it. It's got a ring of gas around it. And you can see this ring is also rotating. We can do something subtler, which is we can take the different frequency data and we can color one a bluish, a warmish blue, a purpley color that comes towards the viewer, and then desaturate it to a non blue over here, but it's desaturated. And so we still have a bit of velocity information when we make an image like this that's a combination of the optical and the neutral hydrogen gas ring. Now I want you to notice here that this is a figure in a paper, but it's simultaneously a public outreach image. So when you make public outreach images, they're not decoupled at all from your research. They still go into your professional papers. Okay, so we can ask the question like, why do these rings form? Do galaxies only form in certain discrete ways? And what is the theory behind that? So on the left here, we have a cosmological simulation where we start with dark matter density fluctuations in the early universe. And then the hydrogen gas actually pools in these dark matter mini halos, because that's where the gravitational pull is. And that hydrogen gets converted into stars. So fuels for stars. And the stars and the gas are gravitationally bound. Well, what are they? They're dwarf galaxies. And the dwarf galaxies encounter other dwarf galaxies, and they orbit around each other and then merge together to form a larger galaxy. And then these larger galaxies merge together and so on. And this is called hierarchical galaxy formation. And as you see here, this is what's been going on in the cosmological simulation. And what you can see is that that things aren't distributed uniformly. Instead, there's kind of a large scale structure is what we call it in astronomy, and what we call it to the public is a cosmic web. So currently, one of our quests is to discover hydrogen gas flowing along the filaments in this cosmic web, because galaxies, even though they form stars and the stars die, there's still gas in the galaxy. And so we know that the gas in galaxies has to be replenished. Originally, we found these polar rings in galaxies using optical telescopes like the Hubble telescope, and we would subsequently use radio telescopes to look for the neutral hydrogen gas, and we would find it then. In one scenario, the gas flows along the cosmic web into the galaxy or into its region and forms stars in the process, and that creates that ring around the galaxy. But this survey, the way we found this one was that it was in a survey. We weren't looking for these rings, and we discovered them. And it doesn't look like it has stars. We found a number of them that are just apparently gas rings. That means they're more polar ring galaxies than we would determine using optical telescopes. Well, we also think there's a hint of stars there. Where are they? There's a hint. So we're looking into that. We're trying to find data or collect data that's sensitive enough to trace the stars. However, there's another way that these polar rings could form. So if you have a group of galaxies or pairs of galaxies, they feel the gravitational pull of each other, they interact and merge together. And when this happens, tidal effects occur. And the stars and the gas are gravitationally pulled out of some of the galaxies and end up orbiting around other galaxies. Perhaps it's a combination of the two, where we have some gas flowing in to galaxies that are interacting and merging together. And so that's a question to be explored. Maybe some of you will find it interesting and turn that into your research with time. This is a public outreach image. So this is my kind of segue into the public outreach images. You'll notice at the top, I call this a Western image tradition image. Those kinds of images are very detailed. First of all, I'll tell you why we do this after, but that kind of image is very detailed. It appears natural. You feel like it could occur in nature. It mimics nature. It's very convincing. It's compelling. It can tell you something like, okay, this region is glowing pink, therefore there must be star formation happening that is ionizing the hydrogen gas. And over here we have young hot stars, which are blue in this tidal tail here. So these images are made for the public because the public does not understand our contour plots nor like them. So we aim for Western image tradition images. So where does this fit in for my work from my professor's contract? Well, there's community work such as public outreach. So I do give talks, but what I focus on is creating content in the form of images. And a goal of these outreach images is to reveal the science in all of those collaborations that I'm in. This is an image that was requested by NASA, and it's a neutron star here, an explosion created a neutron star pulsar, and that, of course, when you have the, pardon me, explosion, you create a supernova remnant here, and the pulsar has been shot out. It had a big kick when it exploded, and it's at the tip of this structure right there. So these are meant to tell you something about science. And we're applying, you can see that there's a lot of spatial depth in this image, and it's because I use that warm, cool approach and recede phenomenon that happens for the eye brain, and the background is cool. Okay, so we can use these images, these public outreach images, for analysis. I mentioned Ron Akers with the postcards. He went from being a director of an observatory to president of the International Astronomical Union. And he points out that this image I made of the Cygnus region, which is just far infrared data and radio data, he points out that this is a detector of black holes in the center of distant galaxies because these little dots here are not stars. They show synchrotron radiation, and the synchrotron radiation is due to electrons spiraling in the magnetic fields that are in the jets coming out of the black holes in the center of galaxies. This is also one of the first images that from radio that was created in Western image tradition. And if you want to see more of my images, there's a website. I don't have the newest ones up there, but you could just look at Jayanne Cosmos Canvas at WordPress, and there's a whole listing of the images. Now, the public doesn't, move this out of the way if I can. The public doesn't find these sorts of images that we have in papers very intriguing. They don't understand contours and they don't understand vectors. So I encourage people to use techniques from visual art to create more appealing versions like this. So we now use an optical image here for the disk of the galaxy. This is by a colleague, Jelena Stein. And for the magnetic field lines coming out of the disk of the galaxy, instead of using vectors, we use something called line integral convolution. So it is an algorithm that uses the polarization angle of light and the intensity of that polarized light to create these lines. So it's kind of like instead of doing vectors, you join up the vectors like dragging a stick through sand, is what the algorithm does. Okay, so the images that we're using originally are not high quality snapshots. They take time to produce, collect, and they're summed together. They're combined in some mathematical way. And we call those original data images logic image data instead of Western image data images. So it's called logic just because logic circuits or counting devices and um, our our devices in astronomy, like CCD cameras and so on, each pixel is a counting machine. So we have scientific information here and we can retain that. So if you want to know how to make a magnetic field image using LIC, you can check out how I made this particular image at NASA's Illuminated Universe. You could probably just go to Illuminated Universe NASA and Google my name, and you'll come up with how the optical image here is made from HST data and how the rest of this image is created and how they're put together. So we discovered that there are magnetic field lines coming out of the disks of galaxies. Now, sometimes people like to say, like to give prestige to these illustrations of the science, but they want to give it prestige by saying a striking image is art. And I often don't feel that way, or I didn't feel that way until one of my most respected instructors at the Ontario College of Art wrote to me this about this image. To be able to picture for us the complexity of a universe that lies behind that image, an image that is itself not an image, but a pictorial representation of forces we can hardly understand, is amazing. We, of course, make convenient distinctions in defining human purpose, but what you make is at its most basic structural level a contribution to the practice of art. So I started to rethink my position on this. Okay, so in the professor's contract, we also have teaching. And so let's look at that one. It's the training of students. And I taught a course called The Art of Scientific Visualization. And I first did that as a guest professor at the University of Zurich. And I did this to science students, not astronomy students. They were microbiology, quantum chemistry, and evolutionary genetics. And one of their exercises was to make a representation of the cosmic web using human perception techniques. And the students came to me and said, we want to put our exercises together and submit them to an art show. So they did, and here we are at the one in Zurich, and they also were in a curated one in Toronto. So that was very nice and successful. So that leads me into mingling art and science, working with artists. There's a good article about how working with artists and residents, because some institutions have an artist embedded in their research groups, how this is very beneficial because scientists aiming for public communication become better observers of their own work and are inspired to approach the research differently. I showed Alexandra Mir, who's an established artist who had two exhibitions in England coming up at major galleries, how to make public outreach images using Hubble data. But she really doesn't like color and she likes marks and gestures, drawing. So we made it the same way with different layers for different wavelengths, different strokes for different wavelengths, and combine them together the same way we combine data from the Hubble Space Telescope. And remarkably, you can still see the structure of the nebula in her drawing, which was very cool. So another thing that happens when you work with artists is that the approaches and techniques that they teach us or expose us to get fed back into the tools we create for our data analysis. And they also, of course, impact our outreach visualizations. So here's another example, Emily Gong. She asked, can we analyze the kinematics of autonomous vehicles using astronomy tools and revisualize the results in traditional painting materials? So I've been showing you the velocity field, and you can see that on the left. It's kind of my color scheme. But really, radio astronomy data of neutral hydrogen gas is three-dimensional. So we have two spatial dimensions, but the other dimension is wavelength or velocity. So we've been taking three-dimensional data and compressing it to display on the computer screen in 2 dimensions. Well, Emily kept it in 3 dimensions and she wanted to paint. So she painted on transparent layers that she stacked up in this small room-sized structure. So it was very large. This showed at the Bi-City Biennale of Urbanism and Architecture, which was held in this museum. It was to be about Shenzhen and Hong Kong, and this is in Shenzhen. And this is great exposure for astronomy because almost 10,000 people attended this Biennale. So when you're doing work with artists, you end up making striking images using techniques from art and design. These have very high hits. So when I post an image like this one on Astronomy Picture of the Day, then I will get 1 million hits the first day. But it's mainly because it's more beneficial to the public. These images are understood more quickly than our vectors and our contour plots. And it's meant to pique the interest of people. And then they'll go off and they'll look up other information about the object that you're showing them. Now, I mentioned that this is really good for Astronomy Picture of the Day, but the people who are going there are already really interested in astronomy. But if you work with artists, they become collegial ambassadors to audiences that would not otherwise be aware of anything that we were working on. So this is a way to expand our audience and get the public interested in our work. And the other thing is when you make an art piece with an artist or a composer, then, if I were to say, let's put my cat's, the stellar fella, Stella, into the paper, they'd say no. But the artist will say, yes, Stella must go into the piece, which is great fun. Okay, so I've covered what the contract is for a professor, and I'd like to make a couple of reflections here. This is another question from that breakfast group. What types of adversity do you face in your work and how do you address them? So if you want to have a bit of a deep picture on that, you can go to Illuminating Science, Art, and Astronomy for All, an interview with Jayanne English. It's at the Faculty of Science at the University of Manitoba, if you don't want to note this link. So you can probably just Google that. And in that, they ask me how I overcame things, what were the issues, and so on. I will say, to make a long story short, that I'm stubborn. So I stuck with it no matter what and no matter how painful the environment was. In terms of making astronomy images, whether it's these maps, catalog figures, or public outreach images, astronomy image making has, for all of that, that whole landscape has changed. When I started with Hubble Heritage, nobody thought visualization was important. And indeed, the scientists that I was working with thought they were more expert at making images than artists were. Now, all these scientists ask for my expertise. And it was wonderful to discover this, that the whole landscape had changed. So, okay, so how did that come about? Well, I addressed the early dismissals of my visualization by giving image making workshops. And I did this particularly to people like you, to graduate students. And I've been at this for a long time. So those graduate students became professors. And so they always liked imaging. And that's how that worked out. Okay, so I want to talk just a little bit about my current research as a senior scholar, because I find it very interesting how my research studies have looped around. Remember, in time, looped around, that my first outreach image was a figure from my thesis, and it was NGC 3256. In that research, I discovered a gas cloud, as much gas as there would be in a galaxy, but without the stars, no galaxy there. And the problem with this is that I've used two different kinds of telescopes. When you're using a radio telescope that's made up of many antennas, an interferometer, you use a Fourier transform to take signal and change it into an image. Well, that can create artifacts. So it looked like I had created an artifact. So I went and got a single dish telescope and stepped it across the sky and found that there was a really strong signal. So people said, well, it's due to this galaxy here. So some people did not believe the veil of cloud existed. There are new astonishing telescopes. The person who I worked with on this project was Bärbel Korobalski. I think she's mentioned down here somewhere. And she said to me, do you want to look at this again now? And that's at the end of my career, just as I'm about to retire. And so we got the data, and using a different telescope and a different way of processing the data, different software, my cloud is still there. So I was very happy about that. It wasn't an artifact. The other thing I'm really working on now is, remember I said that the radio astronomy data was in a three-dimensional cube? Well, instead of looking at collapsing that and even rotating it and making kind of little schemes of it on a two-dimensional surface, which is a computer monitor, we're now leaving it in 3D so that we don't get some misconceptions that are generated when you look at 3D objects in 2D. So how do you do that? How do you look at it in 3D? You use a virtual reality headset. So this is my current work, and we don't know how color works in 3D. I showed you on the 2D screen, the red and the blue, the warm and the cool, but let's see what happens in 3D. How does the brain read that? So here's a little summary. My career trajectory and responsibilities were used to introduce human perception and the impact it can have on data analysis, on discovery science, and public outreach. I used my trajectory to note the benefits of working with artists and to reflect on the appreciation of scientific visualization, how that grew with time. I hope that this talk has been an example of an interdisciplinary career from which you can discover some tips for your own goals. Thank you.
Thank you. A virtual round of applause. Maybe I will stop the recording and then we can go to questions.